This video is a basic introduction to conformational analysis, a field of study of the three-dimensional shapes of molecules. We will use a simple alkane as our starting point. We will see how alkanes change their shape simply by rotating a carbon-carbon single bond. And to help us in this unit, we will first learn how to draw Newman projections. Then we will go into the conformational analysis of ethane and propane. Then finally, the conformational analysis of butane. So conformations are the rotation that is possible about the single carbon-carbon bond that allows molecules to take different three-dimensional orientation, therefore shapes. For example, take the simple ethane molecule. We can see that it can rotate about this single carbon-carbon bond. And upon maybe a 180 degrees rotation, we can have this new conformation. So these are different conformations of the same molecule. So in order to facilitate seeing different conformations and how they have different energies, we will use what is known as the Newman projections. So this structure here is a typical wedge and dash representation. So there are other ways to visualize this molecule. To see these other perspectives, imagine rotating about this axis. I'm going to go ahead and highlight the left carbon and hydrogens to help us visualize in this 3D drawing. So at a 45 degrees angle rotation, we get this sawhorse structure. And if we rotate from the sawhorse structure another 45 degrees, we will get a different structure, a different angle. And in this angle, the front carbon will overlap completely with the back carbon, covering it completely. So we will represent the front carbon as a single dot and the back carbon as that circle. So this is what we call the Newman projection, where again, the back carbon is represented by the circle, and the dot represents the front carbon. Let's go ahead and get some practice with this Newman projection. Let's say you were given this molecule and asked to draw a Newman projection. And to be more specific, a particular perspective is indicated. So we're looking down the bond of the second and the third carbons. So whatever is bonded to these two carbons are of great importance. So we want to highlight exactly what is there, meaning missing hydrogens. Notice that this carbon right now only has 3 bonds. So there must be another hydrogen that's missing. So let's go ahead and draw it in. That goes for the third carbon also. So I like to draw this squiggly line to represent that I'm rotating the molecule in some way. So to start out drawing your Newman projections, I like to draw the circle first and the dot. And looking at the dot represents the carbon in front. Right? So the carbon in front has a line that's going down. So I'm going to go ahead and draw that line straight down. And then take yourself from that perspective. If you were looking down that line, is that bromine going to be on your right-hand side or on your left-hand side? It's coming out of the paper, right? So if you're staring from the left to right and something's coming out of the plane, then that something will be on your right-hand side. So bromine will be in this orientation. And therefore, the hydrogen is on the left-hand side. So notice I've drawn it so that the 3 spokes coming out are equal distance from each other. Okay, now let's go to the back. So notice in the back, the line structure is pointed up. So I'm going to draw it also straight up. And then the bromine, if I stare at it, is coming out again as a wedge. So it is going to be coming out at this angle to the right. And then for hydrogen is going out at this angle to the left. Again, we are going to have that 120 degrees distance apart between those 3 groups. All right, let's try that again. This time, let's draw it if the perspective was indicated from the bottom up. How would you draw this? Okay, so let's go ahead and try it. All right, so I'm going to start out with my circle and my dot. My dot in the front representing the carbon. This time the flat structure, the flat line is pointing up, so I'm going to draw it straight up. And that's my methyl group. This time the bromine, if I'm looking from the right-hand side to the left, the bromine that's coming out is going to be on my left side, right? So I'm going to draw the bromine coming out to the left like that, and therefore the hydrogen to the right like that. Again, they are all 120 degrees apart. Now looking at the back carbon, I notice that the flat line structure is pointing down, so I'm going to go ahead and just draw it straight down. And my bromine again is wedged So from my perspective, it's going to the left. So I'm going to draw it at an angle to the left, and the hydrogen therefore is to the right. Notice that I'm drawing it, the back carbon, the things coming out from the back carbon just to the edge of the circle, whereas the things that are coming out of the front carbon meet right at that center dot. So there you go, that's my Newman projection with that perspective. Again, these two molecules are exactly the same, right? So when you draw a Newman projection, they look quite different, but don't be tricked by that. We're just drawing the same molecule from different perspectives. Okay, so with our Newman projection in hand, let's go ahead and dive deeper into taking a look at the conformational analysis of ethane. So here's our wedge and dash representation of ethane. If we were to draw this in Newman projection, we can see that the front carbons have 3 hydrogens and the back carbon has 3 hydrogens. Let's highlight this hydrogen, this bond, which is this hydrogen and this bond, and the back carbon, which is, and this hydrogen and this bond, which is that. Taking a look at the red hydrogen and the extra line I drew, these 3 points make a plane. Likewise, from the blue hydrogen side, this hydrogen, this carbon, and this carbon, again, the 3 points make another plane. So you have the red plane and the blue plane. And so the angle that is made from these 2 different planes can be seen in the Newman projection quite clearly. Okay, so this angle has a special name. It's called a dihedral angle. And in this case, the dihedral angle is 60 degrees. And as the dihedral angle is at 60 degrees in ethane, we call this conformation a staggered conformation. And it turns out to be the lowest energy conformation for ethane. Now, as the dihedral angle gets smaller and smaller, when it goes to 0 degrees, where the hydrogen in the front overlap completely with the hydrogens in the back from this perspective, we have a different conformation. Let's go ahead and rotate the front carbon clockwise 60 degrees. So the atoms in the back do not move, but the atoms in the front have moved. And I'm trying to draw it so that you can still see it, but technically they are covered completely, right? So if the dihedral angle now is 0 degrees. So as the hydrogens in the front are covering completely the hydrogens in the back are totally eclipsed, right? This is called the eclipsed conformation. So as it turns out, ethane molecule does not like to exist in the eclipse conformation. It turns out to be the highest energy conformation for ethane. The difference in energy between these 2 conformations is 12 kilojoules per mole. This is a significant amount of energy because it translates to the fact that if you're at room temperature, 99% of your molecule will prefer to be in the staggered conformation as opposed to the eclipsed conformation. So this penalty in energy between the 2 conformations is called torsional strain. So the eclipsed conformation has this torsional strain, whereas the staggered conformation is relieved of this strain. And the best explanation for the root of the strain comes from quantum mechanics, but we won't get into it. The simplified version of that explanation is that there is a repulsion from bonding pair electrons. For example, when you have an eclipse conformation, the front bond, which contains a bonding pair of electrons, and the back bond, which contain another bonding pair of electrons, will repel one another. This torsional strain is therefore absent when you have a staggered conformation, when these bonds are not overlaying on top of one another. All right, so we'll use these same images to now take a look at the conformational analysis of propane, adding 1 more carbon to our structure. So instead of that hydrogen being just a hydrogen, now it is a methyl group, a CH3. And so now in propane, as you can see, the torsional strain is not between 2 hydrogens anymore, but between a methyl group, a bulkier group, and hydrogen. So naturally you would expect there to be a little bit more of a strain, and indeed there is more strain. And the difference in energy between the staggered and the eclipse conformation of propane turns out to be 14 kilojoules per mole. So let's continue again to add on 1 more carbon. So now we're going to have a conformational analysis of butane. So now we're going to have a 4 carbon chain. In the same way, in our first conformation, the staggered conformation, it is again the most stable conformation. If we again rotate the dihedral angle to the right again by 60 degrees, you get this eclipse conformation. And as we have seen in propane, the methyl group and hydrogen being eclipsed raise the torsional strain a bit. And now we see in butane the same effect, but even more since there's another pair of methyl and hydrogen eclipsing. So this one actually has a higher energy of 16 kilojoules per mole. But what's interesting about butane is if you rotate the dihedral angle once more, another 60 degrees, you will have a different energy landscape. Again, keeping that back group the same. We see now that this is also a staggered conformation, right? However, it is not the same energy as our first staggered conformation. In fact, our first staggered conformation is the lowest conformation and has a special name. It is called the anti-conformation, and it has the lowest energy. Let's go back to our new conformation here, and it turns out this conformation has an energy difference of 3.8 kilojoules per mole higher than that of the anti-conformation. So if it's in a staggered conformation, what is giving the strain? So instead of torsional strain here, we have a more spatial strain. Remember that the methyl groups, CH3, are quite bulky compared to just a single hydrogen. Because of that, there is a steric strain or steric interaction that exists when two methyl groups are 60 degrees apart from each other in a dihedral angle. So what happens is the electron clouds of these two methyl groups are repelling one another, destabilizing the molecule. So because whenever you have this kind of 3D or spatial interactions, we call them steric interactions. And in particular, when you have two methyl groups interacting each other at this dihedral angle, we call it a gauche interaction. And so therefore, this conformation is called the gauche conformation. And one way for you to remember why it's called the gauche conformation, because the word gauche means socially awkward or lacking ease and grace, right? So if you are two methyl groups, you are crammed together like that, so there's a little bit of discomfort. So that's why it's called the gauche conformation. There's one last conformation that has a distinct energy level, so we'll do that one more time. So go ahead and rotate again clockwise by 60 degrees of the carbon in front. Again, the carbon at back is not rotated, so we will keep it the same. And so this time, we come back to another eclipse conformation. But this eclipse conformation seems doubly bad. It has the highest energy, 19 kilojoules per mole higher than the anti-conformation. And why is that? Well, for two reasons, right? You can see the added effects here. First off, it's an eclipse conformation, so it has that torsional strain. And then further, you have that awkward methyl-methyl close in proximity kind of steric interaction. So we also have that steric strain, giving us the highest possible energy conformation for butane. Now, if you keep on continuing circling that front carbon around, you will see different conformations, but there will be conformations that we have seen already, so I won't go into detail about their energies. You can go ahead and convince yourself of these other different conformations. And in fact, the term here is that they have degenerate energy because they have the same type of steric or torsional strain, so they will have the same amount of energy as one of these conformations that I have highlighted here. Let's go ahead and see a practice problem involving conformations and energies. Let's say you were given this molecule and asked to determine the highest and lowest energy conformation. So we're going to draw the Newman projection. So again, I always like to highlight all of my atoms that are involved in the front and the back carbon. So in this case, the front carbon will have another hydrogen and the back carbon will have two hydrogens. So for my Newman projection, I draw my circle and my dot. The in the plane bond is pointing down, so I'm gonna just point that down, and that's a methyl group. And my other methyl group is a wedge, so it's gonna be going to your right hand side. And then my other bond is to a hydrogen. Now from the back, my in the plane bond is pointing up, so that's going to be straight up. And then my other two bonds are two hydrogens, so both left and right are from the hydrogen. Now, in this one, notice that the back structure has only one methyl group, so it has less methyl groups, so less things for me to redraw. So I'm going to rotate the back carbon instead this time. So for example, if I were to rotate it 60 degrees, what structure will I get? Again, the front carbon doesn't move, so just replicate that. And this time you get CH3 eclipsed. Ooh, that's not good. And then hydrogen also eclipsed here and here. Okay, so again, we see here a pretty bad interaction, right? Not only eclipsed, but also has steric strain, so it has two strains there. So this is definitely going to be a candidate for the highest energy conformation. So let's see if I can rotate that one more time and see if I have a different conformation. So this time my methyl group is right in the middle there. Okay. All right, so let's see, just to take a look in advance here, if I rotate this group one more time, it's gonna go ahead and eclipse this methyl group here. So it's gonna be very similar to this structure, but go ahead and draw it to prove to yourself and convince yourself that's the case. So I'm gonna skip that one, so since it's gonna be degenerate in energy as this one. And if I rotate it again, now the methyl group will be in this position, so it's going to be very similar to in energy to this structure. So again, I'm not going to do that. But go ahead and convince yourself that that is the case. So because of that, I'm pretty sure that these are the three structures I should be analyzing. So let's go ahead and analyze it. For sure, we know the eclipse structure is the highest in energy. So among these three, you only have the middle one is your eclipse structure. So this conformation will be your highest energy conformation. Now, which is your lowest energy conformation? So you have a competition between the first staggered conformation and the second staggered conformation over here on your right-hand side. So remember, because they're both in staggered conformation, they do not have that torsional strain. So we'll have to look for that steric strain, that gauche interaction. In the first structure, we do have one gauche interaction. In the second staggered conformation over here, we have actually two gauche interactions, right? That's doubly as bad. So I would imagine that this conformation will be my lowest energy conformation. Oh, and actually there is another eclipse conformation, but it is not as bad as the one eclipse conformation that we have here. But go ahead and convince yourself that there is one more conformation with a different energy. All right, so there you have it. That completes our discussion on linear alkanes and their conformations.